In computer science, in the context of data storage, serialization is the process of translating data structures or object state into a format that can be stored and reconstructed later in the same or another computer environment. When the resulting series of bits is reread according to the serialization format, it can be used to create a semantically identical clone of the original object. For many complex objects, such as those that make extensive use of references, this process is not straightforward. Serialization of object-oriented objects does not include any of their associated methods with which they were previously inextricably linked. This process of serializing an object is also called marshalling an object. The opposite operation, extracting a data structure from a series of bytes, is deserialization. Uses: serialization provides a method of persisting objects, for example writing their properties to a file on disk, or saving them to a database. A method of remote procedure calls, for example, as in SOAP. A method for distributing objects, especially in component-based software engineering such as COM, CORBA, etc. A method for detecting changes in time-varying data. For some of these features to be useful, architecture independence must be maintained. For example, for maximal use of distribution, a computer running on a different hardware architecture should be able to reliably reconstruct a serialized data stream, regardless of endianness. This means that the simpler and faster procedure of directly copying the memory layout of the data structure cannot work reliably for all architectures. Serializing the data structure in an architecture-independent format means to prevent the problems of byte ordering, memory layout, or simply different ways of representing data structures in different programming languages. Inherent to any serialization scheme is that, because the encoding of the data is by definition serial, extracting one part of the serialized data structure requires that the entire object be read from start to end, and reconstructed. In many applications this linearity is an asset, because it enables simple, common I/O interfaces to be utilized to hold and pass on the state of an object. In applications where higher performance is an issue, it can make sense to expend more effort to deal with a more complex, non-linear storage organization. Even on a single machine, primitive pointer objects are too fragile to save because the objects to which they point may be reloaded to a different location in memory. To deal with this, the serialization process includes a step called unswizzling or pointer unswizzling, where direct pointer references are converted to references based on name or position. The deserialization process includes an inverse step called pointer swizzling. Since both serializing and deserializing can be driven from common code, it is possible for the common code to do both at the same time, and thus, 1. Detect differences between the objects being serialized and their prior copies, and 2. Provide the input for the next such detection. It is not necessary to actually build the prior copy because differences can be detected on the fly. The technique is called differential execution. It is useful in the programming of user interfaces whose contents are time-varying. Graphical objects can be created, removed, altered, or made to handle input events without necessarily having to write separate code to do those things. Consequences: serialization, however, breaks the opacity of an abstract data type by potentially exposing private implementation details. Trivial implementations which serialize all data members may violate encapsulation. To discourage competitors from making compatible products, publishers of proprietary software often keep the details of their program's serialization formats a trade secret. Some deliberately obfuscate or even encrypt the serialized data. Yet, interoperability requires that applications be able to understand each other's serialization formats. Therefore, remote method call architectures such as CORBA define their serialization formats in detail. Many institutions, such as archives and libraries, attempt to future-proof their backup archives in particular, database dumps by storing them in some relatively human-readable serialized format. Serialization formats. The Xerox Network Systems courier technology in the early 1980s influenced the first widely adopted standard. Sun Microsystems published the external data representation in 1987. In the late 1990s, a push to provide an alternative to the standard serialization protocols started. XML was used to produce a human-readable text-based encoding. Such an encoding can be useful for persistent objects that may be read and understood by humans, or communicated to other systems regardless of programming language. It has the disadvantage of losing the more compact, byte stream-based encoding, but by this point larger storage and transmission capacities made file size less of a concern than in the early days of computing. Binary XML had been proposed as a compromise which was not readable by plain text editors, but was more compact than regular XML. In the 2000s, XML was often used for asynchronous transfer of structured data between client and server in AJAX web applications. JSON is a more lightweight plain text alternative to XML which is also commonly used for client-server communication in web applications. JSON is based on JavaScript syntax, but is supported in other programming languages as well. Another alternative, YAML, is effectively a superset of JSON and includes features that make it more powerful for serialization, more human-friendly, and potentially more compact. These features include a notion of tagging data types, support for non-hierarchical data structures, the option to structure data with indentation, and multiple forms of scalar data quoting. Another human-readable serialization format is the property list format used in the XTSTEP, NUSTEP, and Mac OS X Cocoa. For large-volume scientific data sets, such as satellite data and output of numerical climate, weather, or ocean models, specific binary serialization standards have been developed, for example HDF, NetCDF and the older GRIB. Programming language support. Several object-oriented programming languages directly support object serialization either by syntactic sugar elements or providing a standard interface for doing so. Some of these programming languages are Ruby, Smalltalk, Python, PHP, Objective-C, Java, and the .NET family of languages. There are also libraries available that add serialization support to languages that lack native support for it. .NET Framework. In the .NET languages, classes can be serialized and deserialized by adding the serializable attribute to the class. If new members are added to a serializable class, they can be tagged with the optional field attribute to allow previous versions of the object to be deserialized without error. This attribute affects only deserialization, and prevents the runtime from throwing an exception if a member is missing from the serialized stream. A member can also be marked with a non-serialized attribute to indicate that it should not be serialized. This will allow the details of those members to be kept secret. Objects may be serialized in binary format for deserialization by other .NET applications. There are also third-party binary serializers that are documented, portable, use less memory footprint and CPU. The framework also provides the SOAP formatter and XML serializer objects to support serialization in human-readable, cross-platform XML. Objective-C, in the GNU runtime variant of the Objective-C programming language NUSTEP, serialization is achieved by overriding the write and read methods in the object root class. In the next-style runtime used by Cocoa and Mac OS X, the implementation is very similar. Newer versions of Cocoa and NUSTEP also provide a more sophisticated serialization scheme which is referred to as keyed archiving. Java provides automatic serialization which requires that the object be marked by implementing the Java IO serializable interface. Implementing the interface marks the class as OK to serialize, and Java then handles serialization internally. There are no serialization methods defined on the serializable interface, but a serializable class can optionally define methods with certain special names and signatures that if defined, will be called as part of the serialization-deserialization process. The language also allows the developer to override the serialization process more thoroughly by implementing another interface, the externalizable interface, which includes two special methods that are used to save and restore the object's state. There are three primary reasons why objects are not serializable by default and must implement the serializable interface to access Java's serialization mechanism. Firstly, not all objects capture useful semantics in a serialized state. For example, a thread object is tied to the state of the current JVM. There is no context in which a deserialized thread object would maintain useful semantics. Secondly, the serialized state of an object forms part of its class's compatibility contract. Maintaining compatibility between versions of serializable classes requires additional effort and consideration. Therefore, making a class serializable needs to be a deliberate design decision and not a default condition. Lastly, serialization allows access to non-transient private members of a class that are not otherwise accessible. Classes containing sensitive information should not be serializable nor externalizable. The standard encoding method uses a simple translation of the fields into a byte stream. Primitives as well as non-transient, non-static referenced objects are encoded into the stream. Each object that is referenced by the serialized object and not marked as transient must also be serialized. And if any object in the complete graph of non-transient object references is not serializable, then serialization will fail. The developer can influence this behavior by marking objects as transient, or by redefining the serialization for an object so that some portion of the reference graph is truncated and not serialized. It is possible to serialize Java objects through JDBC and store them into a database. While Swing components do implement the serializable interface, they are not portable between different versions of the Java virtual machine. As such, a Swing component, or any component which inherits it, may be serialized to an array of bytes, but it is not guaranteed that this storage will be readable on another machine. CFML allows data structures to be serialized to WDDX with the CFWDDX tag and to JSON with the serialized JSON function. OCaml standard library provides marshalling through the marshal module and the pervasives functions output value and input value. While OCaml programming is statically type-checked, uses of the marshal module may break type guarantees, as there is no way to check whether an unmarshaled stream represents objects of the expected type. In OCaml it is difficult to marshal a function or a data structure which contains a function, because executable code in functions cannot be transmitted across different programs. The standard marshalling functions can preserve sharing and handle cyclic data, which can be configured by a flag. Perl. Several Perl modules available from CPAN provide serialization mechanisms, including storable and freeze Thor. Storable includes functions to serialize and deserialize Perl data structures to and from files or Perl scalars. In addition to serializing directly to files, storable includes the freeze function to return a serialized copy of the data packed into a scalar, and Thor to deserialize such a scalar. This is useful for sending a complex data structure over a network socket or storing it in a database. When serializing structures with storable, there are network-safe functions that always store their data in a format that is readable on any computer at a small cost of speed. These functions are named nstore, nfreeze, etc. There are no end functions for deserializing these structures. The regular Thor and retrieve deserialized structures serialized with the end functions and their machine-specific equivalents. C and C++, C and C++ do not provide direct support for serialization. It is however possible to write your own serialization functions, since both languages support writing binary data. Besides, compiler-based solutions, such as the ODBORM system for C++, are capable of automatically producing serialization code with few or no modifications to class declarations. Other popular serialization frameworks are Boost Serialization from the Boost framework and S11n framework. MFC framework also provides serialization methodology as part of its document view architecture. The C++ middleware writer automates the creation of serialization functions. Python, the core general serialization mechanism is the Pickle standard library module. It is a cross-version customizable but unsafe serialization format. The standard library also includes modules serializing to standard data formats, JSON and XML encoded property lists, limited to PLIST-supported types. Finally, it is recommended that an objects or EPR be evaluable in the right environment, making it a rough match for common Lisp's print object. PHP originally implemented serialization through the built-in serialize and unserialize functions. PHP can serialize any of its data types except resources. The built-in unserialize function is often dangerous when used on completely untrusted data. For objects, there are two magic methods that can be implemented within a class sleep and wake up that are called from within serialize and unserialize, respectively, that can clean up and restore an object. For example, it may be desirable to close a database connection on serialization and restore the connection on deserialization. This functionality would be handled in these two magic methods. They also permit the object to pick which properties are serialized. Since 5.1 Philippine pesos, there is an object-oriented serialization mechanism for objects, the Serializable Interface. R has the function dput which writes an ASCII text representation of an object to a file or connection. A representation can be read from a file using dget. Rebel, REBOL will serialize to file or to a string. Strings and files can be deserialized using the polymorphic load function. Ruby includes the standard module marshal with two methods dump and load, akin to the standard Unix utilities dump and restore. These methods serialize to the standard class string, that is, they effectively become a sequence of bytes. Some objects cannot be serialized: bindings, procedure objects, instances of class I/O, singleton objects and interfaces. If a class requires custom serialization, it can be done by implementing two methods, dump and load. The instance method dump should return a string object containing all the information necessary to reconstitute objects of this class and all referenced objects up to a maximum depth given as an integer parameter. The class method load should take a string and return an object of this class. Smalltalk, in general, non-recursive and non-sharing objects can be stored and retrieved in a human-readable form using the store-on/read-from protocol. The store-on method generates the text of a Smalltalk expression which, when evaluated using read-from, recreates the original object. This scheme is special, in that it uses a procedural description of the object, not the data itself. It is therefore very flexible, allowing for classes to define more compact representations. However, in its original form, it does not handle cyclic data structures or preserve the identity of shared references. For this, various portable and non-portable alternatives exist. Some of them are specific to a particular Smalltalk implementation or class library. There are several ways in Squeak Smalltalk to serialize and store objects. The easiest and most used are store-on/read-from, and binary storage formats based on SmartRefStream serializers. In addition, bundled objects can be stored and retrieved using image segments. Both provide a so-called binary object storage framework, which supports serialization into and retrieval from a compact binary form. Both handle cyclic, recursive and shared structures, storage retrieval of class and metaclass info and include mechanisms for on-the-fly object migration. The APIs are similar, but the encoding details are different, making these two formats incompatible. However, the Smalltalk Xcode is open source and free and can be loaded into other Smalltalks to allow for cross-dialect object interchange. Object serialization is not part of the ANSI Smalltalk specification. As a result, the code to serialize an object varies by Smalltalk implementation. The resulting binary data also varies. For instance, a serialized object created in Squeak Smalltalk cannot be restored in Ambri Smalltalk. Consequently, various applications that do work on multiple Smalltalk implementations that rely on object serialization cannot share data between these different implementations. These applications include the MinStore Object Database, 1, and some RPC packages. A solution to this problem is SIXX, 2, which is a package for multiple small talks that uses an XML-based format for serialization. Lisp. Generally, a Lisp data structure can be serialized with the functions read and print. A variable foo containing, for example, a list of arrays would be printed by. Similarly, an object can be read from a stream named sby. These two parts of the Lisp implementation are called the printer and the reader. The output of print is human readable. It uses lists demarked by parentheses, for example. In many types of Lisp, including Common Lisp, the printer cannot represent every type of data because it is not clear how to do so. In Common Lisp, for example, the printer cannot print CLOS objects. Instead, the programmer may write a method on the generic function printObject. This will be invoked when the object is printed. This is somewhat similar to the method used in Ruby. Lisp code itself is written in the syntax of the reader, called read syntax. Most languages use separate and different parsers to deal with code and data. Lisp only uses one. A file containing Lisp code may be read into memory as a data structure, transformed by another program, then possibly executed or written out, such as in a readd print loop. Not all readers-writers support cyclic, recursive or shared structures. Haskell. In Haskell, serialization is supported for types that are members of the read and show type classes. Every type that is a member of the read type class defines a function that will extract the data from the string representation of the dumped data. The show type class, in turn, contains the show function from which a string representation of the object can be generated. The programmer need not define the functions explicitly, merely declaring a type to be deriving read or deriving show, or both, can make the compiler generate the appropriate functions for many cases. The auto-generated instance for show also produces valid source code, so the same Haskell value can be generated by running the code produced by show in, for example, a Haskell interpreter. For more efficient serialization, there are Haskell libraries that allow high-speed serialization in binary format, for example binary. Windows PowerShell. Windows PowerShell implements serialization through the built-in cmdlet export CLI.xml. Export CLI.xml serializes .NET objects and stores the resulting XML in a file. To reconstitute the objects, use the import CLI.xml cmdlet, which generates a deserialized object from the XML in the exported file. Deserialized objects, often known as property bags, are not live objects. They are snapshots that have properties, but no methods. Two-dimensional data structures can also be serialized in CSV format using the built-in complets import CSV and export CSV. See also, Hibernate, Persister.NET, XML schema, basic encoding rules, Google Protocol buffers, references. External links, Java SE7, Java 1.4 Object Serialization Documentation. Durable Java, Serialization archived November 25, 2005 at the Wayback Machine, XML data binding resources, Databoard binary serialization with partial and random access, type system, RPC, type adaptation, and text format.